Okay, so hopefully this is working. So I'm going to record my screen and hopefully you guys will see this. So hi, welcome to a quick sort of explanation of the setup for this semester. I'm going to go through the slides on my tablet. The most important thing I really wanted to sort of go through is now to mention the big differences, which are the setup and the contact with the tutors and with myself, because we won't be seeing each other. So the differences this semester, as I sort of mentioned before, is that everything is going to be run on your laptops. Now, because the development environment, sort of like I said in my email, is Linux based, and you'll be running everything in a virtual machine, and we're running a graphics program, like a program that creates graphical things, meaning that on a native OS, you would be able to use OpenGL and hardware acceleration. But since we're not running in a native environment, or most of you won't be, we won't get this. And so as a result, you actually need not like a super powerful computer, but you obviously can't use a 10-year-old potato laptop to run the VM in this course. So if the VM is really sluggish, then unfortunately I can't really help you. I can show you some tricks so that you can use not use the VS Code development environment, run straight from the command line. That's a lot quicker, but there's only so much you can do. So the fact that there's no embedded systems and everything's running on your laptop, I'm hoping this won't be a sort of a bad thing for anyone, like a deal breaker, but it might be for some people. So it's going to be up to you whether you actually have the resources to sort of undertake what we offer you, or to undertake the course, right? So because we're not doing embedded hardware, we are going to be more focused on the software side of things. So I'm going to teach you the standard things like Git usage, how you debug code, how you compile code. But because we're on x86, we'll sort of go into more things like PostX, which is the operating system standard. If you're running on Linux, it gives you access to a large lot of multi-threading, communications, all of these sort of things that you also get on embedded systems, but an embedded system, they're a lot more limited. So here in this semester, and also with your projects, you're more open to use any sort of standard C libraries that you wouldn't normally have access to on embedded systems. So that is a slight difference. We don't really have to worry about memory requirements as much, but we still want to apply embedded system principles, or more so real-time operating system principles. Like we want to use all the different sort of same paradigms and programming paradigms, even though we don't really have to worry if we're using the extra 10 kilobytes of memory. Exactly. Now, idea is though, through the FreeRTOS emulator, which I'll introduce shortly, that your code would be very easily ported to an actual embedded system. So the code that you write in this semester should hopefully be very similar to the code that my students write, or people write for an embedded system using FreeRTOS. Anyway, so onwards. So the resources and what we've given you and what I emailed everyone about is a virtual machine. So a virtual machine, for those that don't know, is essentially a container that runs on top of your native OS and lets you run a separate operating system. So in this case, you'll be running a slimmed down version of Ubuntu. So if you need to Google something about the OS, just type in Ubuntu, how do I generate an SSH key, for when you get to the Git tutorial, right? Exactly, the link I have posted in the email, which I would have sent last week, although I sent it yesterday. The VM image is available until the 28th. So please download it like ASAP. Check that it works. We had some issues coming up with it. I originally generated it on a really high DPI screen, and if you have a really low DPI screen, it might throw some errors. So I sent a second link out, which I'm going to do in a few minutes, that should resolve these issues for anyone that does have them. Exactly. So blah, 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 native Linux, Exactly. So then the whole idea of giving you the Linux VM is that I also really don't have an idea of how to use a computer that's not Linux anymore. And as a result, the whole sort of thing that I built up was very heavily Linux based. And I can't offer this to people not running Linux. So as a result, you're forced to use Linux for this semester. But Linux offers, like for programming development, I feel that Linux offers like the sort of like the most knowledge. Like you can really get into learning how 100% of your computer works. And essentially a computer is a very large, very dynamic embedded system in a way. So the emulator that you're going to be using this semester is PostFX. We'll get into more what that means later on. It's available on GitHub. Philip, the tutor, and I are still sort of cramming to get the last issues done. So it should be pretty stable and pretty streamlined by the time you get given it. But it's still a work in progress. So I will mention later on, and the next slide, I think, or next couple of slides, if you do have errors with it, like if you're trying to compile it and you get some sort of an error that's not based on the code you wrote, it should be pretty clear in the error messages. Feel free on the GitHub, it's the best way to sort of track the issues, is open an issue. So if you go into the GitHub page, there'll be a little issues tab and you can click create new issue. There's sort of like a template, fill it out, let me know what's wrong. But yeah, please don't send me issues that are like, hey, I was trying to write to do this and it didn't work. I'm wanting issues that are related to the emulator so that I can hopefully fix them and get them published before other students have the same problem. Both the emulator itself and the libraries that it contains are documented in the READMEs. So like when you go into the GitHub website, there's the page that comes up, that's the README. Also, if you click up the top, there's the wiki. In the wiki, there should also be information. But as well as that, there is the Doxygen generated documentation for the libraries on the GitHub pages page, which is also, if you click on this, let me get my pen, I'll circle it. If you click on this guy, there'll be that documentation. Most of the other stuff you'll really need on setting up and whatnot is in the wiki. We're not really writing like a PDF that we're going to distribute with this stuff. It should be all documented online. Pretty much everything's running through GitHub. So the first step in the course will be due to the Git tutorial, which is also available on GitHub here. It's also on my profile. I will go into, after the kickoff lecture, which I'll record after this, I will go through Git and sort of do a bit of a sort of tutorial. And then this is what it's based on. But this is pre-existing and is documented. The course content, we don't use Moodle. The only thing Moodle is used for in this course is submission of your exercises and your projects. So like uploading the zips. Everything else gets run through LRZ's GitLab, where I will upload things. I will push them as you need them. So go onto here and there's an ESPL group. So the group is made up of 3 repositories. There's course content, which is where I put PDFs explaining like the project, the exercises, practice exams, blah, blah, blah. Then there's a demo project and the tool chain. So the demo project and the tool chain, while you can go through the demo project and read the code, because it's still free RTOS code and is somewhat applicable to the semester, this is the demo project for the normal semester, so meaning that the students are compiling and running this on the STM boards, and then the tool chain is the tool chain for the embedded boards, right? So they're not really applicable to this semester, but the demo project might be useful for people if they just want to read more demo code to get an idea of some things. But the demo code provided with the emulator should be more than sufficient to get you running with most sort of paradigms and concepts in free RTOS, right? The lectures, if you're watching this, will be uploaded to YouTube, blah, blah, blah. So the emulator itself, so this here on the right, this is the sort of non-corona. And this is the corona setups, right? So we're on the left, we're doing the corona setup. The non-corona one, you sort of have like, you have the code here. Oops. So this code here, your project code should be very similar, right? Meaning that I should be able to take a student that wrote the code last semester for the embedded boards, do a little bit of changing and sort of get it compiled and working in the emulator pretty quickly, right? So the code base, the ESPL project code base should be pretty similar, same whatevers, which is hopefully what I'm trying to achieve with this course, is that you're learning whatever is similar, but the underlying stack is changed, obviously, because at the bottom, we're no longer on an STM32F4, like the Cortex M4 microcontroller. We're on some sort of an x86 laptop, whatever it is that you have. So then the stack underneath what we're going to be using, which I will sort of go into a bit more detail, like I'll explain the libraries and whatnot I'll do probably like some sort of like a setups or run through videos on the emulator itself. But the stack itself is this, if you see here, you have this sort of like blue box, which is the FreeRTOS emulator, and it encapsulates event handling, graphics, and FreeRTOS. So as we'll see in the introduction lecture, FreeRTOS is the operating system, but it's not an operating system like Linux or Windows where you have to sort of have this really large installation process. FreeRTOS works in that you take the source files and you compile them into your binary, and that's it. So that's why FreeRTOS is so easily integrated, because it's essentially a bunch of C files that you just compile into a binary. And you can do that on x86 just as the same as you can do it using a cross compiler for a Cortex M4, right? So we have, for instance, there's like the TUM draw library here, but there's a few other ones, but the main one for the graphics stuff is TUM draw. And so these are all built into the emulator. They're all documented the same, like all together, and you'll be using most of them, right? There's some more like, I want to say like advanced stuff like the asynchronous IO library and the tracing stuff, which I developed when I was actually creating it to sort of help myself. I don't think many people will dig right into this stuff, but mainly you'll use the TUM draw library, and this replaces UGFX. So UGFX is an embedded, like a portable embedded graphics library, and I've written TUM draw to sort of like emulate its functionality, meaning you give it similar properties and whatnot. But yes, so no UGFX using TUM draw, FreeRTOS. Now FreeRTOS is the same, completely the same. I'm using FreeRTOS 9.0 source files. They are 100% unmodified FreeRTOS sources, meaning that all of the APIs, all of the function calls, everything are exactly the same as when you would go into Google and type in FreeRTOS create cube, and some page will come up or someone will say, hey, use this function. This is the same. So you don't need to come to the tutors or me and say, hey, how do I use this FreeRTOS functionality on your emulator? The APIs and the libraries are all the same sources. So this is where it should hopefully mean that you can write very similar code. So you're writing C code with the same FreeRTOS libraries, right? The difference is underneath this, FreeRTOS is wrapped in POSIX. So POSIX is POSIX itself is just a set of standards, and Linux implements these standards, multi-threading and sockets, communications, blah, 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 all the things that we have used to get the FreeRTOS sources to be able to create threads, to be able to create queues. This is all done using the POSIX standard and Linux implementation of it. So this is why as well, this emulator at the moment, probably will actually never change, is Linux based because it's wrapped on top of Linux stuff. The graphics itself is done with SDL2, which is a very standard C graphics library. It's not super high function, feature rich, but it does the job, right? We'll be able to get basic squares and whatnot, and you'll be able to program basic games like students have in previous semesters. And yep, all of that runs on top of the x86 system. The software layer in previous semesters was the HAL libraries from STM, so this stands for Hardware Abstraction Layer library, I'm pretty sure. But students never really interfaced with this. And so the same thing should be in this semester, is that you shouldn't really need to modify or go and do POSIX calls or do STL stuff, right? You should be able to pretty much just use the library APIs that we provide for TUM Draw, TUM Event, TUM Audio if you wanted to add sound to your game, and the FreeRTOS, of course. So this should change. So the interfacing to, or like your code should be similar in that you don't really have to do x86, POSIX, whatever, specific code, right? So the virtual machine, apart from being a Linux box, we've also set it up with a development environment that should help people that are quite new to developing code. So the idea is that you can use VS Code to develop. So you'll have an ID, you can use the mouse and click through it, and it's all pretty and stuff, and it'll have code completion and whatnot. Of course, you can, if you're so inclined, use the command line and Vim to really do text editor-based editing. But the IDE should sort of make it simple for people, or simple for people that are trying to sort of get into this more like, I mean, at the beginning, in your bachelor studies, you don't really have much exposure to this stuff. So we're going to try and sort of take baby steps and pre-configure a lot of things. So the IDE should take care of a lot of this for you. Exactly. So each student will need the VirtualBox on their system. If we can't get this running for some reason, like your computer just can't run it or something, unfortunately, I can't help you with this because of the situation, and I'm sort of hoping that every student has a machine capable of running this. If not, I'm very sorry, but I can't really help you. Exactly. So we have documented in the wiki on the FreeRTOS emulator page how to import the VM. It's very simple. It's also sort of outlined. No, it's not outlined in this, but I will also do a tutorial where I download it and sort of set it up on my laptop. Exactly. 4 gigabytes of RAM is good. More, the better. Exactly. So as I was mentioning before, the graphics library sort of tries to copy UGFX. Mainly the documentation, I mean, I hope that it's okay. It was very hard to do all of this very quickly. So the documentation is, I want to say decent, but it's by no means great. I think the most important thing for sort of working with these libraries this semester will be going through the demo code, right? There we've sort of used everything you need to sort of get a basic understanding, and this semester doesn't revolve around creating extremely immersive graphic applications. I want to see that you've used the right paradigms for real-time programming using real-time OSs. Exactly. So they're in this link here. This is sending you to the Doxygen documentation. So this is literally inline code comments in the header, in like the source files that document itself. They're very much like, this is the function, this is what you need to pass to it, this is what it returns. There's not really any examples or anything there. It's very much just like you want to know what data types this function takes, you can find them there. The most for getting to know how to use the stuff, really, for people that are not too familiar with C code and development, go through the demo code. So the demo code is in main.c. We've done a demo example there, as well as on the Pong branch, which we'll get to when we do the Git stuff. There is an old game implementation I wrote to test this stuff, because as well as the draw library, there is a bowl library, I think it's called TUM bowl, and in there is some really basic, you can create wall objects and you can create bowls. It's by no means good. It's very hacked together, but for when you come to create a game, it should give you an idea of how you handle objects in C and how you can do collision detection and all this sort of stuff. So this is sort of just the more examples I can give you, the better. So check out the Pong branch at some point, go through the code. I might get around to making a video where I sort of pull the code apart a bit. Exactly. And before the start of the project, I will try and merge or update the Pong branch because it's quite old. It doesn't take all of the updates and the bug fixes that we've done to the emulator. And so you can look at the Pong branch now, but if you try and run it and there's some issues, please don't just come running to me. I will have it fixed and ready to go before you start your project when you actually start to make your own game. Okay. So other libraries, the event handling. So as we'll see later in the emulator, the standard board, which you'll see in the kickoff lecture, I might actually have one. Maybe not. No. Anyway, this is the board. So this was the embedded board. But there was also like a little gamepad with some joysticks and some buttons on it, right? So it was very much like a little Game Boy sort of thing. Instead of that, now we've replaced essentially the joystick with the mouse and the key and the buttons with the keyboard, right? So you need to still be able to handle events being the moving of a mouse, the pressing of a button. And this is taken care of by the SDL library as well. And it's all done through the TUM event library. So you can use the TUM event API, which is a much more simplified, easy to use API. lots of examples in the demo code. And then there's obviously this TUM ball library, which I said here. It's sort of a basic object drawing, game engine style functions, which you'll need to use. I mean, won't need to use, but I would recommend it instead of writing hacky code. Sort of look into how, like, I'm no game developer by any means, but it's sort of just these ideas that game developers use help. And if you sort of spend a little bit of time looking at how they are used or how they work, your development of the project will be made a lot easier, right? If there's any super motivated students out there and you actually end up sort of like adding features to the TUM ball, TUM events, whatever library, like, I'm welcoming people contributing to this, because at the end of the day, this emulator is an open source project available to the public and collaboration. Send me a pull request, send me an email with your features, and we can look at integrating them. That would be absolutely amazing if some students can, sort of contribute. So on top of the last thing, and which we'll get to towards the project, it still has some bugs in it, which I need to fix in the next weeks. There is a communications library, and so this actually stemmed from me wanting to test how asynchronous I/O happens on Linux, and it sort of actually works as a very good drop-in replacement for embedded protocols such as UART and I2C. Obviously, it's a completely different protocol in that it's not embedded and you don't have to set registers and blah, 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 but you still have like a full duplex communication between two endpoints. One, instead of two embedded boards, you have two binaries running on your computer that are communicating through sockets or whatever. So this is also documented on GitHub, on the GitHub pages. I will create a more comprehensive tutorial on this, because you will have to use this at some point, but I'm going to try and abstract away all of the complexities of running Linux, like running the communications on Linux, and sort of try and abstract it to the level that the STM libraries would abstract it on the boards. I'm more interested in your use of managing communications in like a real-time environment than I am in your ability to pick through documentation and use Linux sockets or something, right? So the last thing to go over is the development environment, which is, as I mentioned previously before, is VS Code. We've moved to this because it seems to be very popular amongst people that use IDEs. One second. So it should be pre-installed in your VirtualBox. When you boot the desktop, there'll be an icon called Visual Studio Code. Double click that, essentially you need to run this cmake command. I'll go through this in my tutorial, because I will do a tutorial straight after this about actually setting up the development environment. These will be here just for reference for when you're later on, because you might not remember these. Essentially, I won't go through them right now. I would rather go through them in my little tutorial, which I'll do in a minute. So essentially, the other big difference this semester, apart from the whole environment, the development, and the fact that we won't meet each other, is that you have a tutor as well, Philip. Great guy, knows his way around a keyboard. He is available for officially 4 hours a week. Whether we need them all or not, there's no fixed 4 hour period for him. We're not really sure how to manage this semester, but we're going to try our best to sort of do it on the fly, whatnot. So essentially, Philip is your point of contact for this course, meaning if you have a code problem, please contact Philip. I'm there to help, but I'm the worst case sort of scenario. I don't imagine there'll be any problems you have that Philip can't fix. But if you have admin staff, come to me, and I'm always there to help, but I'm quite busy. So Philip, I'll think on the next slide, I'll say how we can get in contact with him and whatnot, but Philip's your guy. If you're having, like I mentioned before, issues with the emulator itself, you can talk to Philip. And if you know exactly what the problem is, or if you're pretty certain it's with the emulator, just go to GitHub, open an issue, because I am responsible for maintaining the emulator. So of course, if it's some sort of a big critical bug that I've left in the emulator, let me know as soon as possible, and I can fix it so that it can benefit everyone. Essentially, the main means of communicating between students and between you guys and me and Philip is through TUM chat. So it's Rocket Chat, and the website, I think, is this a link? I'm not sure. If you Google TUM chat, I think it's like chat.tum.de or something. Essentially in there we have a channel, ESPL. So if you just search for it, ESPL, you'll find it. In there, we want to sort of set up that you guys can talk to each other, because as much as we would love to help you solve all your problems, answering problems over like chat and video calls and stuff is a lot slower than when we have our normal classroom meetings at TUM. And so we're hoping that you can also sort of help each other a bit to make this load a little less for the teaching staff. So we really want to encourage helping each other. If you have a question, post it there, and if you know the answer, feel free to help your peers. Essentially, that'll be, and also TUM chat will be your main point of contact with Philip. If you have issues that require really showing him your code, blah blah blah, we can also use Elatset's Meet. And to do video calling, screen sharing or whatnot. But firstly, talk to Philip, and then if he says, oh yeah, we should go into video chat and you can show me your screen, then he'll tell you, yeah, we'll go to this room and whatnot. He can take care of this for you. Set up documentation. This is all sort of showing feedback. Philip is there. He should already be in the channel. This is his Elatset. If you want to mention him specifically, like do a little blah blah blah. Hey, I've got this problem. Can you please help me? As far as the times go, we sort of decided normally we'd have a 4-hour chunk on a Wednesday, like at TUM, but because everyone's going to be sort of doing this at their own pace, at their own time, we thought we'd split it up. So these are the times that Philip has put forth. Really, his tutoring time hasn't been set fixed, because the idea is more that if you have a question, you send him a message and he'll try and get back to you and sort of distribute his help, because he's obviously also stuck at home. But these 2 times are sort of like the recommended periods for like this video calling. But really, just reach out to Philip, and then you and him or whatever can set up a chat if the problem's more serious. But yes, we want to really encourage you to help each other, because I think for some students this will be more of a dive into the deep end than for other students. So that's the end of the sort of the differences for this semester. So now I'm going to essentially just switch to my laptop like normal and record how you set up the IDE. So go through this slide. In-screen recording. Okay, see you in a sec.